Okay, in this problem, we need to find out how much heat is needed to convert 876 grams of H2O at 10 degrees, negative 10 degrees Celsius, 226 degrees Celsius. You're given the specific heat of water at the different stages when it's a solid, liquid, and a gas. You're also given the heat diffusion of water. That's the energy needed to melt 1 mole of a solid to liquid. And it also gives you the heat vaporation, which is the energy needed to vaporize 1 mole of liquid to gas. I did a little chart right here, kind of saying how it's going to go. It's going to start off at the freezing point. It's going to go right here. It's going to be at a plateau. That's the melting point. Then it's going to go to all liquid, and then it's going to change until it gets right here, another plateau, and that's the boiling point until it turns all to gas. This will all kind of come clear later on in the problem. So the first thing you got to do is figure out that's what the different Q's are. Different heat at different stages, and it's the summation of those heats is the answer. So we begin by Q1. But before that, we have the heat during a temperature change, which would be these little lines right here. It's Q is equal to mass times specific heat times change in temperature from one point to the next. Then the heat during these plateaus, the melting point and the boiling point, those are during phase changes, kind of. That Q is the change in the heat fusion or evaporation times the number of moles. So right here I already converted the number of moles of our H2O, the 876 grams by the molar mass divided by, give you your moles of water. Now we can go on to figuring out our first Q. Q1, which would be from negative 10 degrees Celsius to 0, because that's the freezing point. So it's mass times specific heat times change in temperature. And then the specific heat was given up here in the problem at our different stages. So it's a solid, a liquid, and a gas. So we'll use those specific heats when we know the different changes of phases. Right now it's a solid, so we plug in all the variables, and that gives us that as our heat for that. Then we do the heat fusion at 0, because there is a phase change right here. So that's going to be our Q2, which would be our heat fusion, which was given earlier, times our number of moles of water, which we solve for up here, gives us our Q2. So that's Q2. We still need 3, 4, and 5. For 3, it's from 0, freezing, up to 100, which is boiling. So we do the mass, which hasn't changed, but the specific heat has, since it's at a liquid form now, and the difference of temperature from the final minus initial. Plugging in those, we get our Q3 for the temperature change from 0 to 100. Notice that all these are in kilojoules. This is our heat evaporation at 100 degrees Celsius, which is this plateau right here. So it's the energy needed to jump over that little plateau and go to the next change. So it's the heat evaporation constant times the number of moles, gives us our Q4. And we have one more, which is our temp from 100 to 126. Again, mass hasn't changed, but our specific heat has, because it's at a gas now, times our temperature difference, which gives us our last heat measurement. Then to figure out the total heat needed for that complete change from negative 10 degrees, which is here, all the way to 126, which is here, you just add all these units together, which are all in kilojoules, which gives you a total of 2.705 to the power of third kilojoules. That's the total energy needed to do the change.